Introduce our next speaker, Professor Kazunori Ueda from the University of Waseda in Japan. I've had the pleasure in the last few years of having many wonderful interactions with Professor Ueda. His interests are at the intersection, or the union maybe, of cyber-physical systems and programming languages. For a long time, he has been very interested in declarative programming languages in particular, and was part of Japan's fifth generation computing project. And now his interest is very much focused on HIDLA, a very interesting programming model, specification, and model for hybrid systems, which is a powerful tool for describing all kinds of aspects of cyber-physical systems. So in the spirit of short introductions and without further ado, I welcome Professor Ueda.
Okay, thank you for the introduction. Okay, so I'd like to talk about the language and system we are developing. So this whole summer school is about cyber-physical systems, but there are some, intersection and some difference between hybrid systems and dynamical systems. So I'll be mostly talking about the modeling of hybrid system here. Okay, so of course I know there are some other interests and concerns in cyber-physical systems, but we are now more interested in modeling some dynamic systems with some continuous and discrete behavior. Okay, so people who are interested in the computational foundations for hybrid systems are divided into two categories. One is to design some foundations for interacting with the physical world, which is to implement cyber-physical systems. The other branch is modeling and simulation and verification of cyber-physical systems. And today I'll be talking about the second aspect, modeling and simulation and verification. Okay. So maybe also almost all of you know hybrid systems, which is or cyber-physical systems. And so the key issue here is the modeling and interacting with the physical world. So, and the physical systems and the computer systems are quite different. So in physical systems, people talk about differential equations, while computer systems, people talk about some difference equations. And the domains they handle are mostly continuous, but sometimes they approximate physical phenomena using some discrete notions. Also, and they talk about mathematics with some differential equations, or sometimes differential plus algebraic equations. And they are mostly concerned with the notion of time. Okay. While as a computer science people, we mostly talk about discrete domain, and we are very interested in programming languages, and we almost always talk about algorithms and abstraction. So there are very clear separation between these worlds. Yeah. So the question is how to reconcile these two interests and concerns with some computing abstraction of physical systems. So basically, I belong to the right category, but I'm trying to approach or reach this left part. That's my basic background. So actually, and today also we already had the name of Edward Lee, and he wrote a very enlightening article called "Cyber-Physical Systems Are Computing Foundation Adequate?" It was published more than 10 years ago, but in that paper, they suggest around 10 challenges, but most of which are not yet properly addressed, I think. And let me choose maybe 4 of them, of the 10 challenges. So one is his first challenge was putting time into programming languages. Yeah, that's quite very important for cyber-physical systems. And maybe the next 5 are more about the operating systems concerns. But the next one is some predictable and controllable and understandable concurrency. Because in many programming languages, the concurrency constructs are much more complicated or hard to understand than sequential constructs. And the next one is about concurrent components. And so this is related to some composition of or modular development of cyber-physical systems. And the next one maybe is about networking, but the last one is some computational dynamical systems theory. So this is to take the physical world people to the computing world people. So in this background, I have been trying to address these challenges for the last several years. So, but anyway, the hybrid systems are systems whose state can make both continuous and distinct changes. So even without computational components, we can see many dynamical systems which exhibit some discrete behavior. The most typical example is a bouncing ball or a billiard. But with some controller, the second one is again quite typical, which consists of thermostat and air conditioner and room. And the third one is again about some control. And so the system with traffic signals and roads and cars. So there are many, the cyber hybrid system comes in many flavors. Okay. But in general, hybrid systems are dynamical systems whose description involves some case analysis. So, so some hybrid systems are cyber-physical systems, and some are just physical systems, and some are just biological systems. So hybrid system covers all these areas. And the difficulty of hybrid systems is that it relates to not just to computer science, it relates to control engineering and applications. So to master hybrid systems. I haven't mastered hybrid systems at all, but anyway, to be familiar with hybrid systems, we should learn many things. Yeah, and that's one of the difficulties. And the final remark is that I personally think that the programming language aspects of cyber-physical systems are rather unexplored. Yeah, so there are many more things to do. So here are some challenges and questions from my point of view. So one is to design and implement programming or modeling languages for hybrid systems. I will later explain the difference between programming languages and modeling languages. So the first question is, what are the basic notions and constructs? So maybe most of you know that we already have a nice theory about hybrid automata. But in the case of computer science, automata is a basic model computation, but it is not enough for programming. So in the case of computer science, we also have lambda calculus, for example, as the foundations of high-level programming languages. So what we are trying to find is something like a counterpart of the lambda calculus for hybrid systems. Okay. And so the next concern is that because we have both continuous and discrete components, so maybe most people think that we should expect that the theory and practice of hybrid systems are significantly more complex than continuous or hybrid discrete systems. So my concern is to keep it simple. So the research question is that can the language for hybrid systems be simple and accessible for non-specialists. Because we should, in this area, we should talk to engineers outside computer science. So I think the formalism should be as simple as possible. So, so now in designing languages for hybrid systems, maybe we should, there are two things to consider. One is about the primitives. So the language constructs which determine the underlying computational model. So this is more about close to something like the lambda calculus. And the other is about this more software engineering point of view. So how to achieve abstraction and how to build a large model with some small components. So, and this is more close to the user language, but in this particular talk, I would like to focus on the first part. So there have been many proposals about the model and languages for hybrid systems. And the first thing we had is a hybrid automata and several other hybrid models, including hybrid petronets and hybrid I/O automata or hybrid process algebra and so on. So these are all some computation models. And also we had several modeling languages and tools with some equations, including differential equations and some notion of updates for discrete changes, which include Modelica or Acumen by Professor Taha, or Ptolemy by Edward Lee, or hybrid language for Andre Pretzer. So it's a shame to mix all these languages because these languages are quite different. But anyway, there are many attempts in having some languages. But today I'd like to focus on language or programming paradigm based on constraints. So, so constraint-based languages are languages whose central construct are equations or inequations, not assignments or some control structures. So yeah, actually, so the view of the constraint programming is that model or programs are just a set of constraints, or maybe the disjunction or conjunction or implication between constraints. So, so there are several attempts to apply the idea of constraint programming into hybrid systems. So when we focus on some solver or verifier, so they maybe ISAT is the most well-known and solver, as constraint solver for hybrid systems. And the first particular language based on constraints for hybrid systems are hybrid concurrent constraint programming by Vijay Saraswat. And also the next one is some constraint logic programming language over real world functions. So F stands for functions over reals. Okay. So all these languages appeared in 1990s. And also the Kaleidoscope is a well-known language. This is a discrete time. This is not a hybrid language, but this is one of the first constraints-based languages which addressed the notion of time. And now our group is working with the Hydro language, which is based on the constraints over real-world functions, and also it comes with the notion of hierarchy. So in the next few slides, I will give you a very quick overview of what this constraint program is. It is a branch of the declarative programming paradigm, in which a problem is described using equations or inequations over continuous or discrete domains. So this is a very broad area. But this is a very typical constraint program, which can be found in some AI artificial intelligence textbook about the solutions of 5 queens. So so the problem is to find the placement of 5 queens over the chessboard of 5x5. So in this case, we should first decide to use 5 variables whose domain is between 1 and 5, which stands for which row each queen will be placed. Okay, and there are some constraints. And if I and j are different, then the placement of the j queen and the placement of the I queen should be different. So they should be placed in a different row. And also, the next two constraints stands and says that the the 2 queens should not be placed in the same diagonal. Okay. And then there are a lot of constraint solvers which, given this set of inequations, gives you the solutions, or the all solutions of this constraint satisfaction problem. Okay. So this is a very classic example. So here, one good point is that in order to obtain the answer, you don't have to write algorithms. You just write specification. Yeah. So actually, the first important point is that in constraint programming, the users don't have to specify algorithms. So constraint programming languages are often called modeling languages. So because when you mention programming, then maybe application people don't like to use it. Yeah, so modeling is a more preferred term in the world of constraints. Okay. And the whole paradigm was developed in the artificial intelligence and partly in the logic programming communities. But in these communities, the central interest has been constraint satisfaction and constraint propagation to solve something like some puzzles or some operations research programs. But if you just search or Google constraint programming, and then you will find some Wikipedia page which lists many libraries for mainstream languages. But the constraint programming languages are not so many, but these languages are mostly based on logic programming. So this is a sort of the mainstream and understanding of constraint programming. But here's another view in constraint programming. So it is computing with partial information. And it uses some notion of symbolic execution. So in this talk, this view is very important. I mean, say, because so each piece of information is some partial information about the placement of constraints. And the combination of all these constraints gives you some answer. Okay. So as I said before, the constraint programming comes in different flavors applications. So most people are interested in constraint satisfaction problems, CSP, and over some finite domain or real domain or some interval domain. So maybe when the Professor Luke Jordan comes, he will talk about interval constraints. Okay. Also, the recent trend in constraint programming is some SMT solvers, which are heavily used for the analysis or the verification of mainstream programs. And the SMT belongs to constraint programming. The difference is that the CSP people are mostly interested in the conjunction of constraints, while SMT people are interested in the complex combination of conjunction, disjunction, negation, and implication. But so in some sense, this is a stronger framework. But they are not very interested in general, in computing some most general solutions, where the CS people or the logic programming people are interested in the most general solutions over the set of constraints. So this is the second trend. And So, and I belong to the third category. So I have been working with a constraint-based concurrency, or what people say concurrent constraint programming. So here is some interpretation or computational interpretation of some logic or logical connectives. So as Professor Boy says that for example, we use so in the case of programming languages, we always have the notion of abstraction or hiding, and the existential quantifier has a computational is a interpretation of hiding, or maybe an interpretation for the fresh name creation. There also the conjunction is the composition of two concurrent processes, and the implication is used for synchronization of concurrent processes. And the interprocess communication can be done using by the telling and asking constraints, as I will explain in the next slide. Okay, also, sorry, this is not the next slide. But recently I wrote the article about the whole history of the constraint-based concurrency, and also the Japanese fifth generation project, which was mentioned by Professor Taha. And so the article will be available very soon. In the Science of Computer Programming journal. Okay, but this is the history of the whole framework, which started in late 70s or early 80s, and there are many languages which was developed in 1980s or 1990s. And actually, I was involved in the language called guarded form clauses, and it's several descendants. But some languages are developed in this country, like Oz and Mozart, and also some others are also developed in Sweden. But in this history, there are some languages which address the notion of time or notion of continuous changes, which are called time concurrent constraint programming or hybrid concurrent constraint language. And our language is very close to this language. So there is some connection. Okay, so let me briefly introduce my very old language. And so this is the how we can compute the factorial of 5 in our constraint-based framework. Okay, so in this case, in our framework, the factorial is not a function. It is a relation. But it is a relation with some direction of computation. So suppose that this is some process or concurrent process, and which observes the value of n, and which determines or constrains the value of n. And here, there is some store of constraints. So maybe you can think of this as a shared memory store. And it is partly correct, but it is partly not correct, because this is a store on the value of variables which are immutable or single assignment. So there is no notion of updates. So there are many variables and many equations, or many inequations. But the point here is that this constraint store stores some constraints on immutable variables. So suppose that this constraint store contains the information m equals 5, then this will be observed by this process or agent, and this agent will eventually publish the constraint n equals 120. And maybe this constraint itself may have been generated by some other constraints, some other process, and maybe this constraint may be observed and used by other process. And so there are no notion of sequential execution between processes. So all processes are concurrent. But there is some causality between the constraints observed by this process and the constraints generated by these constraints. So, so this is program has no notion of time, but maybe this program is a bit related to the framework presented by Professor Breuer. Okay, so suppose you want to compute a sequence of the behavior of the inverter, then maybe with some clock, then maybe the input to the inverter will be a sequence, possibly infinite sequence of 0 and 1, and its output may be possibly infinite sequence of 0 and 1. And here is some program which looks like a logic programming, but and it has some direction. So maybe this information should be observed, and this information may be generated. So there is a clear distinction between what are observed and what are generated. Okay. And because we are mostly talking about the infinite sequence, so you may have some base case, but it is not necessary. So even with this base case, the program makes sense. So, and this suggests that some discrete event systems can be represented using some possibly infinite list. So this is an example of a possibly infinite list, whose first 5 elements are 0, 1, 1, 0, 1, and this A stands for some unknown, part of the yes.
What is where all of this true?
True. Okay, sorry. So this is some so to make it clear that this is not a prologue program. We just put some guard notation, and true is just a no condition. Okay, so the computation goes from left to right. Okay, but not right to left. So this is what is different from the maybe prologue representation of the inverter.
Okay. That's a typo
Yeah.
error. It's a typo error, right?
Sorry?
The series is right.
Series. Yeah.
The third number.
Third number. Oh, so this is correct. Incorrect. Okay. So this is a nice inverter. Thank you very much. Okay. So, so basically, the constraint-based concurrency works like this. So suppose that we have this inverter which accepts an infinite sequence of binary numbers. Then if this observe this constraint, then this will publish this constraint and terminates. And if the input is empty, the output will be empty. And if the input is some partially instantiated list, then the output will also be some partially instantiated. But there is some residual. So after this computation, maybe this inverter will remain, and we will be waiting for the further information about X prime. And if there is no information available, then the inverter will be just suspending. And the information is strange, and then it will generate no information, but there is no chance that the computation will proceed any further. And if some other guy says that y should be 0, then then this inverter will publish the constraint that the first element of y should be 1. So the interesting point in our formalism is that once somebody publishes n equals 120, and if some other guy publishes the information such as n equals 121, then this constraint store just is broken. And once it is broken, anything can be observed. Because if you because you have assumption, if you have the assumption like 1 equals 2, then any logical formula can be deduced. So we have to be very careful not to make this collapse. So this is the basic idea of constraint programming. So now let me go to the hybrid systems. So now let us try to apply this idea into the constraint programming of function over time. So I think this is a generalization of constraint programming over infinite sequences. Okay. And now in our language Hydra, we inherit many features from constraint-based concurrency. For example, we use implication for synchronization and for some conditional branches. And we use conjunction for parallel composition. And we use existent quantification for hiding. So this is a very simple Hydra program. So which says that, so maybe this is some fragment of the car controller. So the first symbol, this is the linear temporal logic notation, which stands for the always. So at any time, if the controller receives the signal of emergency stop, then the derivative of the speed should be minus 4.0, of course, or something like that. So implication has some computational interpretation, which says that if something is known or observed, then something should be done. So this is implication has some causality, and so I think so this is not the classical logic implication. So maybe that. So if you have so in classical logic, we have if we have this, then we have, of course, we also have this, but this doesn't apply. So maybe some people know that when we are talking about some lazy students, so maybe if so, this is a story about a lazy student. If he's not scolded, he will not study. So, but this is not. This doesn't fit much very well with classical logic, because if we take the contract positive of this formula, then study implies scolded. So something is strange. So can somebody explain what is strange about this? So because this and this should be the equivalent formula, but this looks strange. Can you see why?
If you study, you get scolded.
Yes. He studied because he was. Because he was scolded. So there is some difference between cause and result. Or okay. So there's a similar thing happens here. Okay. So the goal is our goal is to establish some high-level programming and modeling language, which are equipped with the notion of continuous time and also the notion of continuous changes. And also, another concern of us is that because we are handling physical world, which has some sort of uncertainty, and also the computing continuous quantities comes with some errors of computation, as long as you use some floating point numbers. So the whole framework should properly handle some uncertainties and some errors of real values. Also, the fourth challenge, which is very important, is that our values, which we handle, almost always have some errors. So, but still, we have some notion of conditionals if then else. So the framework should properly handle conditional branch under uncertainties and errors of real values. So real values. So, for example, we should be able to somehow compare the quantity like this and quantity like this. If it's easy to compare this uncertain value and this, so this is higher, this is lower. But when the uncertainties just overlap, then it's not clear how to decide whether this value and this value, whether this value is larger than this. So we should have some answer to this question. And the next concern is that we should be equipped with some constructs for abstraction and parallel composition. And then we want to establish some semantic foundations of all these. And also, we are going to implement all these ideas. So we have 10 more minutes. So maybe, and let me give you some demonstrations in the final part. So in the next 3 minutes, I will talk about some more motivations. The one is that there are many hybrid system simulation tools, and some guarantee accuracy and some not. But maybe many of you know that for some simple programs, maybe which are not dynamic hybrid systems, but which are dynamic systems, but even without discrete changes, some ordinary simulation with a standard simulation tool cannot yield a single significant digit. So there is a gross errors in computation. And the things are worse in hybrid systems because simulation of hybrid system is particularly hard and can very easily go wrong in a qualitative sense due to conditional branch. So, and there are some technique for rigorous simulation is very important. Maybe you know this example. So this is the example of multiple collision. So there are two balls here, and we just roll this ball this way, and then a very slight change in the trajectory can result in very different bouncing directions. Okay. And also, you know that some cyber-physical systems are safety critical or mission critical. So now there are some more slides, but I think it's better to leave these slides to the next lecture. And let me give you the first example of the language Hydra. So actually, the motivation of this language is to use some popular mathematical or logical symbols like equality or implication as much as possible. But we have something new. So maybe this symbol is not very special. This is a very standard temporal logic notation operator. And maybe this is the only new symbol here. But anyway, let me explain this example one by one. And let me conclude this talk by the demonstration. Okay. So this program consists of 4 lines. And the first 3 lines are rules. And the last line is a combination of rules. Okay. Then the first rule says that, so actually, and this program specifies the trajectory of the function f. So this is not a single variable. So actually, the f is, or all variables in this language is a function over time. So this f is actually f of 0 because all the specification is about the property of the function f at time 0. Okay. So this means that f is equal to 0 means that the initial value of f is 0. Okay. And the next rule says that always the derivative of f is always 1. Okay. And the third rule says that maybe this is a new notation. As f minus is the, so suppose that f is a continuous function, then f minus is the some left limit of the function f. So if the value of f is about to reach 1, then f becomes 0. So there is no destructive assignment because this is the left limit and this is the current value. So so there is some immediate drop from almost 1 to 0. Okay, but this happens infinitely many times as long as the value of f is reaching 1. Okay, this way. Okay. Now we have 3 rules. So the initial condition is okay, but at each integer second, the constraint, the second constraint and the third constraint are not compatible with each other. So because at the 1 second or 2 seconds later, the value of f cannot have derivatives. So we have to we cannot take the conjunction of these 3 rules. So we have to put some priority between these rules. So here is how we put priority between increase and drop. This means that if increase and drop are compatible, then both are just enforced. But if increase is not compatible with drop, then increase will be just forgotten temporarily. So, and also init is the highest constraint, so it is almost enforced, and drop is of the highest priority, so it is almost enforced. So this is a program, and so so here's some review. Okay, see, this program describes property at time 0, but these temporal operators allows you to specify the property at and after time 0. Okay. And the time arguments are implicit. Also, this always operator means for all non-negative time, f prime of t equals 1. And f minus stands for the left-hand limit of f. So let me run this program using our system. So actually, the system is already publicly available. And here's some program with some different parameter. Okay. So maybe maybe then it's easier to read. Okay. So this is a program, and to run this program, we put this button. So it is run, and actually this is a simulation up to 10 phases, and the program just the execution alternate between some continuous phase and some discrete phase, like this way. Actually, the key point here is that this is not a numeric simulator, and it's a symbolic simulator. So the actually before rendering this graph, the output is like this. So there is a bunch of symbolic result of symbolic computation like this. Okay. And now maybe in the next talk, I will talk about a bit more interesting example, like what happens if the initial value of f is something like this. Then let me run this program. Then this looks like the same, but when we just okay. So now, we can also simulate the program with some uncertainty initial value like this. So what happens if the initial value of f is between 0 and 5? So here we have 5 lines, but these lines are just renders from the single execution of the program.
I have one.
Yeah.
The lower limit.
Yeah.
The dash equal to 3.
Sorry, excuse me.
The second line, increase.
Increase, yeah. So in this case, the slope is 3. Okay, yeah.
The slope is 3.
3 plus 3, yeah. And the upper limit is 10. Okay, yeah, yeah.
Upper limit is clear.
Yeah.
How do we know it's 3?
It's 3. Okay, and so 3. Maybe this 3 are zeros. So I think this slope is 3. Yeah, yeah, yeah. Okay, but here the now you can view the if not a single trajectory but a family of trajectories like this. So so there are many interesting examples, but also and it is possible there are some animation here. So to see if the speed of each trajectory is the same or not. So in this case, all trajectories just proceed in the same pace, but in some cases not. Okay. So actually, the difference between the ordinary and the symbolic computation is that when we adopt symbolic computation, we can start with totally unspecified or some uncertainty initial value. But we still, the system still allows you to compute something using some uncertainty constraints. And if you want, you can also include some uncertainty in the slope or the upper limit. Yeah. So, okay. Yes. In this case, the simulation by default stopped at the 10 phases. Yeah. So if you want to compute more, then you can say that you want to go up to 20 phases. Yeah, like this, and also and like this. Okay. So, but the interesting point is that if the So this is the case where the trajectory is totally unspecified. Sorry. No. This one. So this means that so in this program, you cannot tell what value of f at some particular time point will be, but still the this graph retains some information. I mean, so the trajectory is always somewhere between 0 and 10, but there is some dependency. So even in this program, you will verify that each trajectory moves between 0 and 10, and they will not stay just inside this zone. So this solution retains much more information than just the rectangular zone between 0 and 10. Okay. So this is what we are aiming for. Okay. So maybe yes.
What does the horizontal axis represent?
This is in this case you can choose. In this case, the x-axis is time t. So t is some reserved variables standing for time, and this is the value of f. And if you want to go 3D, then you can also use the z-axis like this. But in this case, f is just this is just 2-dimensional. Maybe later I can show you some 3-dimensional demonstration.
If I'd like to have non-deterministic behavior also in the derivative, for example, the derivative that could be either 1 or minus 1. What do I have to write? So it's
actually,
like in the previous example of the sawtooth, but with 2.
Actually, there are several ways to specify some uncertainty. Some discrete uncertainty. So one is to use the equation for the solution is either 1 or -1, like x squared equals 1 or something. And the other solution is that the system tries to adopt as many constraints as possible. Yeah. And so if some constraint, well, some rule says that the slope is 1, and if another rule says that slope is -1, and we put all them in the same line.
Possible to,
Yeah,
we
yeah.
can give like
Yeah.
in the unit you given with a range.
Right, yeah.
The same way can we give it in the increase the slope also like -1 to +1?
Okay, so there are many ways. Yeah, but let me answer to the Professor Moji's question is that if you have different rules governing the slope, and if you put these two rules in the same line, and then the system tries to adopt the maximally consistent subset of rules. But clearly, the slope equals -1 and slope is +1 is not consistent. The system will adopt one of them. And the system comes with some non-deterministic exchange mode. So the system will try to search all possible solutions. Okay. Yeah.
If f is 0 and the increment is 3, and our limit is 10, so we have two constraints, but when f is 9, and then we wanted to increment with 3, so it will violate the other limit. So we have two constraints that one must be violated.
Oh, sorry. So the slope is 3 in this case, and the so okay.
And we wanted to reach f equal 10.
Yes. Yeah.
So we have to violate one of the constraints.
Yes.
The increment or the limit.
Okay. And the thing is that the drop is at the top of the constant priority. So this will be so at the time 3.33, and this constraint. So this constraint is always enabled, but because this is almost always false. So actually this is not enforced. But once this becomes true, then this is enforced. And that when this is enforced, then there's some discrete change between 10 to 1. And so at this point, the f cannot be differentiated. And so this increased constraint will be temporarily invalidated. Okay.
So when there are potential inconsistencies like the ones you described, do you generate warnings for each and every of them?
Okay, so some potential inconsistency is everywhere, every time. So that's part of the specification. But if the whole constraint store becomes not consistent, then it is something strange. So the system will warn you. Okay. So any other questions? So actually, this is okay. Yes. Actually, maybe in the next lecture, I will show you many more examples. So, for example, the bouncing ball is much more interesting than this. Okay. But this is just an introduction. Okay. Also, in the next section, lecture, I will talk about some semantics. Also.
I think I'll hold it to the later session.
Very good. So with that, thank you very much.
Okay, my pleasure.